Hey there, chemistry students. We have video 16-3 that we're on, and its topic is thermochemistry. We've been talking about heat, and we're moving right along with the unit. Real quick review, temperature. Remember, we're measuring the average kinetic energy of molecules. We measure the heat that these molecules produce in joules. And a new term here that you need to make sure you pause the video and write down is calorimeter. This is a device that you will be making in lab to look at how much heat is transferred based on either absorption or is being released, looking at chemical and physical changes. And that's what this video is talking about. It's talking about endothermic and exothermic processes of chemical and physical changes. So make sure you write this down. Quick review, if you need it for Celsius to Kelvin conversions, remember if we have 10 degrees Celsius, that converts to 283 Kelvin. We do not say the degree sign for Kelvin. 30 degrees Celsius converts to 303 Kelvin. We just add 273 to each one of those numbers. So that's a simple conversion that you need to know how to do. Moving along with the review, I want to sum up and ask this question. Are kelvins bigger, smaller, or the same temperature as Celsius? And the answer here, it's identical. 1 degree Celsius equals 1 Kelvin. Something else I want you to know and be familiar with is this absolute zero. When you hear that, what does that mean? Well, it means there are absolutely no movement of particles. And do we ever reach that? No. Almost in outer space, but absolute zero on Earth you will never reach. It's just too much energy to be removed from the system. So continue to move on here. We want to look at some basics here of energy. Really, kinetic energy. Again, it's a review. If you don't know kinetic energy is energy of movement, write it down. Otherwise, I want to take a look at kinetic energy in an example. So in a chemical reaction here, what happens? Well, I wrote this reaction out. We have two H2, which is two hydrogen gas molecules. Remember, a molecule is two or more elements chemically combined. So we have two or more hydrogens. They can be the same or different elements chemically combined for two hydrogen molecules, plus one oxygen molecule yields two water molecules. I want to look at what happens in this reaction. So on this side over here, this is what we call the reactants on this side. And the reactants, we have the oxygen element and another oxygen bonded together right here. O2, that's O2, they're bonded together. Well, what happens is the O2 has to split. So right here, it splits, all right? And we get that split to occur, and we're looking at, well, how much energy occurs for those two oxygens to be tore apart from one another. And we can explain that here. How do you determine that? Well, we can do that mathematically. And that's identifying, was it exothermic or an endothermic reaction? When we take those gas molecule and we rip them apart. And again, that requires you to know the definition of exothermic, which means it gives off energy. Exo on the outside, giving off energy. What is endothermic? Make sure you pause and write this down. Endothermic, taking in energy. We take in the energy when it's endothermic. And we can explain this graphically. And we can look at a graph to basically explain how do these oxygen atoms get ripped apart from one another. And that is splitting of a gas molecule. So right here we have two charts, and I want to zoom in really quickly here on this first one. This first one, let's look at our axes first. That's the first thing that you should do. This is energy. So energy increasing on the way up, and reaction progress, which means it's time. Time going across, all right? So we're increasing time across on the x-axis. Right here, energy required to break bonds of the reactant. So this is what I was talking about, an oxygen atom and an oxygen atom side by side, and they are going to be broken apart there. So that ends up forming an oxygen plus an oxygen. They're separated. Well, when we get these guys that are separated by themselves, after so much time passes, they end up right here. They end up at this point. So they start here at basically what we can call 0, and they end up here. So there's an increase. From here to here, there is an increase. And it's above the x-axis, so this is a positive increase. We don't know the number. It's not labeled. We just know it's positive. And for right now, that's all we care about. We know that there's energy being released as the bonds in the products form. So as we form water later on, that's what we're talking about. Right now, we're looking at just breaking, again, these two together, ripping them apart. And we call this delta H positive, which is endothermic. And we will look at this here in a second in the next slide, but it's an important thing to just introduce right now, that if it's above the x-axis, it's positive, it's endothermic, which remember, endothermic, you're taking in energy, okay? Now look here at the same exact typical graph here, but now where are we ending up? We're ending up down here, right? So this is the 0 point as well. The reaction progresses, gets to a peak, and then it starts forming the products. And down here at the bottom, now we are negative. We're below the x-axis, so we are negative, and we say delta H is negative, which is exothermic. Remember, exo means giving off heat. So when it gives off heat, it's exothermic. Just remember, below the x-axis is negative, okay? Real quick, I want to take a second and watch a video on real-life examples of how endothermic and exothermic processes affect your life. And one video that basically we can use here is airbags and looking at them in your vehicle. So let's watch this short clip.
Airbag is a rapidly inflating cushion that helps to prevent auto crash injuries. When there is a sudden deceleration of the auto, a switch is thrown which triggers the start of a chemical reaction that produces a gas. The chemical reaction employed is the thermal decomposition of sodium azide, NaN3. Upon heating, sodium azide decomposes rapidly to form sodium metal and nitrogen gas. The reaction is exothermic and rapid once it has begun.
So right there, she said the reaction is exothermic, and once it has started. So some type of products here expand, exothermic, giving off energy, they expand. We know that a gas, when heated, expands, and it fills up your airbag, and that's what saves your life. So that's just a real-life example here of this graph right there, exothermic. It's giving off energy, and again, in this process, ends up saving our life, which is really important. All right? Let's keep moving on here and look at some more specific examples to kind of help you understand this a little bit. Now, for enthalpy and enthalpy change, let's take a look here. Enthalpy, you need to write this definition down. Pause the video, write this down. That is H, the total amount of heat energy in a substance. We cannot directly measure this, but you can measure its change. This is the symbol delta. If you do not know that, write that down. Delta means change, all right? Delta H, it means change. So that's change in heat. Enthalpy change, which is here heat, the total amount of energy a substance contains, the change in the amount of energy it's either absorbed or released. So remember, endothermic, exothermic, releasing energy. We can calculate that. Change in enthalpy is the heat of the products minus heat of the reactants. What you finish with minus what you start with. And I just showed you this in the graphs, that delta H is exothermic when it's negative. That means it's giving off energy. Or delta H is positive and it's endothermic. It's taking in energy. The plus and minus signs indicate the direction of the heat flow. Again, endothermic there, it's absorbing heat in. Exothermic, negative, giving heat off. You need to know. It's very important to know that. And we'll look at some examples here of these types of reactions. Again, jot this down. plus heat is absorbed from the surroundings. When it absorbs from the surroundings, I just said what that was. What type of change is that? You should have been able to answer that. Endothermic, right? It's absorbing energy. It's on the inside, endo. When it's negative, we know heat is released to the surroundings and it becomes exothermic. It's being released. So delta H negative, exothermic. Make sure you know that. It's very, very, very important. Quick review. The conservation of energy. Energy can never be created or destroyed. You have to know this. If you haven't written this down or put it in your notes, put it in there. And put this in here in your notes as well. If it's endothermic, how can it have more energy in the end than in the beginning? Well, something else has lost energy. In order for it to gain energy and bring energy into it and be endothermic, it has to take the energy from somewhere else. Because energy cannot be created or destroyed, it has to take it in. So think about that, and we're going to look at some examples of endothermic and exothermic examples.